Hello. In this lesson, we're going to talk about mathematical induction method. Before we start, we'd like to show you an example of a conjecture. Conjecture is something that we have observed. It seemed to be true, but it has not been fully proved. For example, okay, in this example, you're going to observe, okay, we're going to observe some interesting phenomena. Okay, so I'm gonna put some rows in here, just 2 columns. Okay, just 2 columns to see if that's enough. So what we're gonna do is we look at the sum of the first odd numbers. Okay, sum of first number of odd numbers. Okay, for example, we know odd numbers are odd numbers. So what are the odd numbers? 1, right? The second odd number is 3, 5, 7, 9, and so on and so forth, right? The next one is 11, 13. If we keep going, we actually see a pattern, right? The first odd number, of course, I'm going to put it in a table so you can observe that. Okay, so this table, I'm going to make it multiple columns, but only 2 rows. Okay, so the first one, of course, is 1. The second one, okay, the second one is 3. The second one is 3. Okay, but 3 is actually 2 times 1, or 2 times 2 minus 1. The first one, okay, just follow me very carefully. The first one is 2 times 1 equals 1. So because we're showing you a pattern of these odd numbers, so the first one is the first times 2 minus 1. The second one is second times 2 minus 1. The third one is the 3, 2 times 3 minus 1, which is 5. Okay, so this one, the first one is 1, of course. So we're just choosing a different form to write our odd numbers, right? So first, second, third, right? We express it in a common form. That common form is 2n minus 1. And what is n? N is the first, in the first case, second, okay, second, which is going to be 2. So in the case of second, n is 2. In the case of third, n is 3. Okay. So let me show this to you again. So you use this pattern. Okay. For the first one, we will take 2 times 1. The 1 is from here. 2 times 1 minus 1. Okay. So the 1 here is from the first here. Okay. From the 1 here, the order. Okay. So this is the first odd number. Second odd number is the second, right? Number 2, we take number 2, multiply 2, and minus 1, we get 3. So that's the second odd number. For the third odd number, we take the third, n equals 3. 3 times 2 equals to 5. And the fourth one, okay, fourth one is that we're going to take the 4. We know the fourth one is 7, right? The fourth one is 7. But 7 is also equals to 2 times 4, the fourth one, minus 1. Okay, the fifth one. Okay, this is very much showing you how to find patterns to express numbers. So the fifth one now, n is 5. So we take 2n minus 1. 2n minus 1. And we know we should get 9. We should get 9. Okay, but 9 can also be expressed as 2 times 5. The fifth, 2 times 5 minus 1, that's going to be 9. So for 6, for the 6th odd number, okay, and you got it. I think by this time you got it. We should have 11. So, but 11 is expressed as 2 times 6. So 2 times 6. 2 times 6, 12 minus 1, that's 11. So that way for 13 and so on and so forth. So the 7th one, right, as you can see, is going to fall on the same pattern. It's going to fall on the same pattern. We know the 7th one is going to be 13. It's going to be 13. And 13 is also equals to 2 times 7. The order 7's, 2 times 7, minus 1, that's 13. So this pattern will continue and forever and ever. Okay, and next we're going to look at the sum of first odd numbers. Okay, the sum of first odd numbers. For example, the sum of first one number. Okay, the sum of the first one number. What would that be? Okay, I'm going to put this over here. Okay, the sum of first odd number. First odd number, which we only have 1, right? So 1 is, of course, equals to 1. But the sum of first 2, okay, the first one odd number. How about the sum of first 2 odd numbers? Of course, in the first case, we only have a singular, we don't have plural. The sum of first 2 odd numbers, meaning the first one and second one, the first 2. So that's going to be 1 plus 3. 1 plus 3. 1 plus 3 is 4. Okay, and then we continue to observe the sum of first 3 odd numbers. And that's going to be 1 plus 3 plus 5. And that's going to be 9. And if we continue to observe the sum of, okay, so I'm going to put this as 2, okay, the sum of first 4 odd numbers, and that's going to be 1 plus 3 plus 5 plus 7. So that's going to be 1 plus 3 plus 5 plus 7. And what do we get? We get 16. And if we look at the sum of first 5 odd numbers, 1, 2, 3, 4, 5, right? So 1 plus 3 plus 5 plus 7, and add another one, which is the 5th odd number, that's going to be 25. And we keep going, okay? And what do we observe, right? So what have we observed? We found that this is a 2 squared. And 9 is 3 squared. Okay, and this 3 agrees with this 3. Did you notice? And this 2 agrees with this 2. And 16 equals to 4 squared. And that 4 agrees with this 4. okay, the sum of first 4 odd numbers. And the 5, of course, you can see it agrees with 5 squared. Okay, then how about 6? Certainly we can go on one more. And the question is, now we're gonna come up with some conjecture. We're guessing, okay? The first 6 odd numbers, so now we have the first 5 already, right? We just need to add one more, right? And that's gonna be 25 plus 11, and that's 36. And 36 is 6 squared. Haven't we found a pattern? And what is more, if we look back the entire sequence we have here, 1 is equals to 1 squared. So our conjecture is that right? Our conjecture is it true? Is it true, right? It seems that the sum of the first n odd numbers, the sum of first n odd numbers, right? The first n odd numbers, the sum of the first n odd numbers. What are the sum of the first n odd numbers, right? The sum of first 5 odd numbers is going to be 1 plus 3 plus 5 plus 7 plus 9. The last number is 2 times 5 minus 1, remember, right? So the sum of first and first until the fifth, and you can see we're just adding these numbers. We're just adding these numbers, adding the first 5 numbers. So now the sum of first n odd numbers is, okay, 1 plus 3 plus 5 plus, if we keep going, okay, we start making guesses, right? We observe the phenomena up to 6, okay, the first 3. Then you say, what if the first n? The first n, the nth one would be 2 times n minus 1. Would this be just n squared? That is the conjecture. So we're guessing, even though we have seen this phenomena is true, okay, it is true for 1, 2, 3, 4, 5, 6, and we're guessing that it is going to be true for any n, the first n odd numbers. So this is called a conjecture because we cannot prove it. We human can only do finite number of activities. We cannot do infinite, right? So what then you say, well, yes, it is true for the first 6. Maybe it may not be true for the first 10,000, right? Are we going to do the first 10,000? Sure, you can prove it's true for the first 10,000, but can you guarantee it's true for the first 20,000? Right? So that requires even more. So we will never be able to do as many as possible. Okay, so we need a procedure to prove it. So mathematical induction method has come to answer this, this demand, is how we can develop a procedure to allow this process, okay, to keep going. Okay, it's going to be true for 7. So what you see is that in this process, right, in the first case, it is obviously true. In the second case, it's obviously true. So can we prove that for anything, if for any case that's for, say, it's true for a second, can we take the case true for a second to prove that the third case is true, okay, to allow this process keep going and forever true? So this is a mathematical induction method. So here is the principle of mathematical induction. Okay, it has three, well, it has actually basically 2 steps. Okay, some say 3 steps. Okay, but primarily it's really just 2 steps. Okay, first of all, we have to specify the conjecture for each natural number. So now this procedure is for natural number, for each natural number, n. So what are natural numbers? Do we know what natural numbers are? Okay, natural numbers are 1, 2, 3, 4. The counting number does not include 0, unless otherwise specified. Okay, excuse me. If n is a natural number and there's a statement, okay, there's a statement. Be a statement depending on n. Okay, suppose that the following 2 conditions are satisfied. So what are these 2 statements? Satisfied. Okay, the first statement is that the first statement, okay, is true for n equals to 1. Okay, so P of 1 is true. Okay, i.e., the statement is true for natural number n equals to 1. Second, okay, for every natural number k, provided P of k is true. Okay, so there's an if. Okay, so we make an assumption, say P of k is true. Is true. Then P of k plus 1 is true. P of k plus 1 is true. So we make an assumption on the second step. Okay, we make assumptions that P, the statement is true for k, and then we get to prove that P of k plus 1 is also true, and then we can conclude. Then P of n is true for all natural number n. Okay, so let's explain this. Okay, let's explain this. For example, our first conjecture, right? So in the example, right? Example, this is our conjecture. Our conjecture is that the sum of the first n odd numbers is going to be n squared. So this is the statement. This is the statement. Okay, this is the statement. And the statement says that the sum of first n odd numbers is the same as n squared. Okay, the sum of first n odd numbers is the same as n squared. So that we call it P of n. So in word, that's the word. And in mathematical expression, that we add the first n odd numbers and we get n squared. So this is the statement. And then now we're going to go about to prove it. Okay, so we're going to go by 2 steps. Okay, step 1, we're going to prove that it is true for n equals to 1. N equals to 1, and that is obvious, right? When n equals to 1, the left-hand side, right? When n equals to 1, the left-hand side is 1, the right-hand side is also 1. Okay, so the left-hand side, which is only 1, which is 1, and the right-hand side, is 1 squared. So equals to 1. So left equals to right, then you can say it is true for n equals to 1. Step 2. Step 2, we're going to assume it is true for k. Okay, and k is arbitrarily any natural number. So we're going to make assumption. We're going to say assume, okay, the statement, which statement? The statement which is here. This statement is true for k. The statement is true for k. What does that mean? Well, this statement, right, if we turn everything for k, right, n becomes k, we assume it is true. So here, there's no proof. There's no proof. We assume it is true. But then we're going to prove, okay? And we now, to prove that it is true for k plus 1. For k plus 1. So what is to be proved, right? So to be proved, what are to be proved? To be proved are these. This is to be proved. Okay, so let me put it over here on the same line. To be proved is a k plus 1. Oops. K plus 1. And that's going to be k plus 1. Okay, all the n turn into k plus 1. And this is going to be k plus 1. Whoops. N squared. Okay. So the case for k plus 1 is 1 plus 3, which is the first k plus 1 odd number. And that's how we express it, right? That's how we express first, the second, third, and the k plus 1s. And that's 2 times k plus 1 minus 1. And we want to prove that this is true. So this is to be proved. To be proved from what? From this assumption. And the first case is already proved true. Okay, so now we're going to start. So once we have identified what is to be proved, so we're going to take the left-hand side. Okay, we're going to take the left-hand side of the to be proved. And we're going to work it out. Okay, we're going to work it. We're going to work it. Well, the first k plus 1, right? 2k plus 1 these odd numbers, right? Let's organize them. 1 plus 3 plus 5 plus the last one is 2k plus 1, 2 times k plus 1, right? And we're going to organize this term to figure out what's in front of it, right? So that's 2k plus 2 minus 1. So this is going to be 2k plus 1. So what is the odd number before 2k plus 1? In other words, the first k odd number, right? The first k odd number, of course, that's going to be 2k minus 1, right? 2k minus 1. Okay, so we're adding these odd numbers. We're adding these odd numbers. Okay. Excuse me. So now we're going to apply the assumption because we assume these are the first k odd numbers, right? So we're going to regroup these numbers, and these are the first k odd numbers. The first k odd numbers, according to our assumption, is a k squared. Okay, so in the bracket, we get a k squared. We apply the assumption, and then the additional 2k plus 1. And of course, we're going to remove the parentheses, factor, and we will get k plus 1 squared. So it is now proved. What have we proved? We have proved that it's true for k, so for n equals 1. And if it is true for k, it is also true for k plus 1. Okay, which is just what's required by mathematical induction method. So having proved these two steps, okay, so then we can say that this fact, right? We can now say that statement. We can say now this statement is true for all natural number n. So this allows us to keep going that process forever and ever. So this is the mass induction method. We're going to use the mathematical induction method to prove a couple more very useful sums that you're going to use in calculus 1. Okay, in calculus 1, the first one. Okay, so we're going to do that. The second example. Example number 2. Okay, so we are to prove that the sum of a first natural number. Okay, the sum of first natural number. What are the sum of first natural number? The sum of first natural number is 1 plus 2 plus 3 plus all the way to n. The first n natural number is equals to n times n plus 1 divided by 2. Okay, and you're going to use this this formula in your calculus 1 class, okay, and we're going to prove it using mathematical induction. Okay, so here's the proof, right? There's 2 steps. First, we need to prove it's true. Okay, it's true for n equals to 1. Is it true for n equals 1, right? When n equals to 1, the left-hand side, is equals to 1, right? The first one natural number is 1. And the right-hand side is this piece, but n is substituted by 1 because n equals to 1. And now it is 1. So left equals to right. So this is true for n equals to 1. And then we get to step 2. Okay. In step 2, we assume the statement is true for k. What does it mean? The statement is true for k. Well, this statement, n turn into k. The first k natural number, the sum of first k natural number is such. Okay, and to prove, okay, what do? We prove that this statement is true for k plus 1. Okay, so n turn into k plus 1. K plus 1, sorry. And n turn into k plus 1. And n turn into k plus 1. Okay, so if we simplify the right-hand side of the to be proved, and we will get k plus 1 times k plus 2. So this is to be proved. Okay, so we know the true is true for n equals to 1. We assume it's true for k. So now we're going to prove it's true for k plus 1. Okay, so this is a k plus 1 case. So now it's going to start from the left-hand side. Okay, and we can remove this. So the left-hand side of the to be proved, okay, the left-hand side of the to be proved is such. And of course, before k plus 1 is a k, isn't it? It's a k. And for this part, we can use the assumed fact, right? The assumed fact says the sum of first k, right? So we're going to take these and group the first k together and apply what is true, what is assumed to be true for the first k. So we're going to put it here, n plus k plus 1. Okay, so we have applied the assumed, the assumed. Okay, this is the assumed. And now let's keep going to see if we will end up to be the right-hand side here. Okay, so next we're going to factor. We're going to factor. Okay, we can find common denominator, right? Or we can do this. Okay, divided by 2, multiply by 2. 2 times k plus 1. So this way we get the same denominator. And the same denominator, we're going to take it out as 1 over 2. And in the bracket, right, we have this product multiply 2 times k plus 1. Okay, you can see we already have the divided by 2 here, right? We have divided by 2. Okay, we just have to prove the inside the bracket is the numerator of the right-hand side of the to be proved. Okay, so we're going to keep the half together. We're going to keep the half outside. And inside the bracket, we're going to distribute k times k is k squared. And k times 1 is a k. And there's another k. And there's another 1, right? So now we get k squared plus 2k wait, I think this is 2. Sorry, this is 2. So this is 2K, this is 2. Okay, so this is 3K, sorry, 3K plus 2. 3K plus 2. And if we factor the inside the bracket, we will have 1/2 times K, K plus 1 times K plus 2, which is exactly the right-hand side. Then you say that is, right, we have proved it. We have proved it. We have proved it. We start from the left-hand side. We ended up on the right-hand side. Okay, then you can say, therefore, that statement, right, the statement here is true for all natural number n. This statement is true for natural number n. Okay, so this is the sum of first n integers, the sum of first n natural numbers. And the other two, there are 2 more we're going to prove. Okay, there are 2 more we're going to prove that these 3 together, you're going to need them in your calculus class. Okay, so the next example we're going to prove, okay, is the sum of the sum of squares. Okay, the sum of squares of the first n natural numbers. So what are they? 1 squared plus 2 squared plus 3 squared. So you square the first n natural numbers plus n squared. It is going to be equal to, okay, it is going to be equal to n times n plus 1 and times 2n plus 1 divided by 6. And we want to prove that it is true for all natural numbers. For natural number n. So we're going to use the mass induction method again. We're going to use the mass induction method. Okay, we're going to use mass induction method. The first one, of course, is the step 1. We're going to prove it's true for n equals to 1. Okay, so step 1, true. The statement is true for n equals to 1. Is it true, right? So then you just show the reader, right? The left-hand side. The left-hand side. Left-hand side when n equals to 1, it's just 1 squared. Right? 1 squared is 1. And the right-hand side, what's on the right-hand side? The right-hand side is this piece and replace n by 1. Okay, replace n by 1. 1, right? So this is 2 times 3, 6/6, that's equals to 1. So it's true for n equals to 1. Step 2, assume the statement is true for k. Which means, right? Which means that this statement is going to be true for k when n is substituted by k. That's true for k. And we are going to prove it's true for k plus 1. So when n is replaced by k plus 1, and n is going to be replaced by k plus 1. Okay, all the n are replaced by k plus 1. So this is n replaced by k plus 1, and this n will be replaced by k plus 1. Okay, I'm making the fonts just a little bit larger. Okay, so let's take a look at this. Okay, let's take a look at and we simplify this form a little bit. Okay, so when we simplify this, we got k plus 1, right? And over here, k plus 1 and plus 1, so that's going to make it k plus 2. So this is a k plus 2. And the next one is 2k plus 1. So if we distribute the 2, we get 2k plus 2. Okay, 2k plus 2. 2k plus 2, then plus 1, that's 2k plus 3. Okay, so that's to be proved. That's to be proved. So we want to prove the left-hand side is the same as the right-hand side. So this is our task next. So we're going to start from the left-hand side. Okay, which is right here. And the term before k plus 1 squared obviously is going to be k squared, right? And we're gonna apply the assumed, right? So we're gonna take this entire thing on the left-hand side, and we group all of the first k terms together, apply the assumed. The assumed says 1 squared plus 2 squared plus all the way to k squared is this piece. So we're going to replace that. We're going to replace the bracket, okay, everything inside the bracket by the assumed equal and plus k plus 1 squared. So now from here, we want to prove it's going to be the same as the right-hand side. Okay. So now what do we do? What do we do? There are a couple of things we can do. Number one is that we can make a common denominator. Okay, and you can see from what we want to go, from where we want to go, it's going to be a factor form. So we're going to factor this entire form. Okay, so firstly, we're going to make it a common denominator. Okay, we already have the denominator 6, right? And so we're going to factor out what we can. Okay, we're going to factor out what we can. So what can be factored out? We can factor out the 6 in the denominator. What else can be factored out? K plus 1, right? There's a k plus 1 here, and there's a k plus 1. There are 2 k plus 1 here. So we're going to take 1 k plus 1 outside. Now in the bracket, right? In the bracket, 6 is out, k plus 1 is out. So we just have k times 2k plus 1. Right, and the other one is 6 times k plus 1. Okay, and then what? We got the next. Okay, the outside is already in the factored form, and part of it is what we want, right? K plus 1 over 6, we already get that. So we just have to organize the term inside the bracket and to see if they can be factored into these 2 factors, right? So we got 2k squared plus k plus 6k plus 6. Okay, and then We organize the inside of the bracket, combine like terms, that is. Okay, combining like terms in the bracket, we get 2 times k squared plus 7k plus 6. And can we factor that into, can we factor that? Of course. Okay, of course. So this will be factored into exactly k plus 2 times 2k plus 3. Okay, you can verify. You can verify. Right, you can verify. How do you verify? You take this piece, you FOIL, right? You FOIL that, and you should get 2k squared plus 7k plus 6, right? So that's pretty easy to verify. And we got the right-hand side, okay? And then you can say, i.e., it's true for k plus 1. It's true for k plus 1, okay? You say the statement is true for k plus 1. By this time, we have completed all steps in mathematical induction. So you can say, therefore, right? The statement is true. What statement is true? The statement is true for all natural number n. So this is the mathematical induction method that has proof. So next, we're gonna prove the one more, which is in the or another one that we're gonna use in calculus 1, okay? But this time is 1 to the power 3, 2 to the power 3, 3 to the power 3, all the way up to n to the power 3. Okay, well, what does that equal to? It equals to 4 n squared multiply n plus 1 squared. So that is to be proved. Okay, so the sum of the sum of cubed first natural number is equals to that piece, And okay, so if you like to pause and try your own, and this is the time to do so. Okay, I hope you have tried on your own. So let's prove it. Let's prove it together, okay? If you find any mistakes I made here, then you should contact me. Okay, so first, of course, we want to prove it. We're going to do step 1. Okay, the statement is true for n equals to 1. And usually this case, it's pretty easy to prove, right? So you can see the left-hand side. Left-hand side is equals to 1 to the power 3, right? That's equals to 1, right? And the right-hand side, is going to be the entire right-hand side and replace n by 1, right? And that's going to be 1. So left equals to right. True for n equals 1. So step 2, we assume the statement is true is true for K. What does that mean? It means that these statements, okay, is going to be true for K. So N is replaced by K. And then what we need to do is to prove the statement is true for N plus 1. So this is going to be N plus 1, or K plus 1, sorry, K plus 1. So all the N now are replaced by K plus 1. So N is replaced by K plus 1. And over here, N is replaced by K plus 1. K plus 1, then plus 1, that's K plus 2. So this is to be proved. Okay, so this entire statement is to be proved. So once again, we're going to use the proved case in case 1 and the assumed truth for, at the beginning of step 2, and we're going to start from the left-hand side. Okay, and on the left-hand side, okay, and of course, before K plus 1 to the power 3 is a K to the power 3. Okay, so we have been using the same technique, right? But it's really important that you know these facts and you're going to need to use them in calculus 1. And over here, we're going to regroup. Okay, we're going to group the first K terms. And the first K terms, we can apply the assumed. Okay, so the bracket replaced by the assumed plus K plus 1 to the power 3. And we're pretty much using the same trick. Okay, we're pretty much using the same trick. Make the common denominator. Right, multiply 4, divided by 4, and factored out the 4, along with other common factors. So 4 in the denominator is factored out, and we have a K plus 1 squared, and here we have a K plus 1 to the power 3, so we factored out the K plus 1 squared, right? So inside the bracket, K plus 1 squared over 4 is factored out, so we have K squared, right? On the other parentheses, we're going to have 4 times K plus 1, 4 times K plus 1, K plus 1, and there we go. We got a part of it already, right? K plus 1 squared over 4, already get that. So we kind of know where to go, right? We know where to go because we know what is to be proved. We just have to make sure it is happening indeed. So that's K squared, not K to the power 3, I'm sorry. K squared plus 4K plus 4. And that is a perfect square. Right, we're pretty familiar with that. So in the end, inside the bracket is K plus 2 squared indeed. And you can always verify by foiling, by FOIL. Okay, so we got the right-hand side. So then you can say that is, you tell the reader, hey, I have proved it. So this has been proved. It's true for K plus 1. Okay, so now conclusion. Therefore, okay, the initial statement is true for all natural numbers. We follow the induction method to the T's. Okay, so we follow the induction method to the T's. There are a lot of other mathematical induction proofs that we can do, but I think for this lesson, we're going to do this much. I'm going to do one more for math induction method too. So you're going to see some other cases, some other studies that might be useful, and it will be using slightly different methods. We're going to be using slightly different methods. Okay, So without further ado, and I think we're going to end this lesson for now and look for the next one. And thank you for watching.